So I wanted to talk in this lecture about the extra sum of squares principle and regression modelling assumptions. So for the extra sum of squares principle, what this is a lot of f-tests, so a slightly different and more systematic treatment of some of the topics that you've seen before. As regards regression modelling assumptions, these are important for two reasons really. So in the past, when I've set exams and courseworks, it's been useful to have something that is about attention to detail and attention to written information that's quantitative in nature, not necessarily numerical, and to sort of give people, practice at sort of useful skills, analytical skills for accounting and finance that doesn't necessarily involve overt calculations. Also, what I think is important here is that if you could treat regression modelling assumptions systematically in your dissertation, then that is beginning to push towards the limit of what you could naturally expect project students to be able to do. Okay, so there's two reasons really why these regression modelling assumptions are important. Firstly, I think it's sort of good analytical skills and a sort of non-mathematical component of the course. Secondly, if you can master them, you'll begin to push against the limit of what you can expect project students to do. So in terms of background reading then, so I've said here chapters 4 to 8 of this book by Gujarati and Porter. Now, again, I will try and make my lecture notes self-contained. I'm also going to try and turn these notes into a book, so you should have quite a lot of good resources available internally as part of the module. Shouldn't be too much extra need for additional background reading beyond that. What I wanted to say here is that you have to be aware, I think, on occasion that the book by Gujarati and Porter does have some technical limitations, or it does have a very good selection of topics. Okay, and then just to recap, so the resources you've got on this, so you've got these PDF lecture slides, these lecture recordings, and also the PDF study book. So you should hopefully have quite a lot of resources available, though obviously not ideal circumstances at the moment for teaching. Okay, so this is the sort of background reading that I've suggested externally, but I've got quite a lot of resources, so hopefully you should be able to get by to a large extent with just the resources that I'm going to provide you as part of this course. So in terms of the outline of the lecture then, so the first thing I want to talk about is this extra sum of squares principle and give some f-tests and talk about some mathematical formulae. Now, this is necessarily then an extension of some of the material we've seen in the last lecture. I'll give some examples. Hopefully you should sort of see that the bark is inspired really with this sort of stuff. I will then talk about the regression modelling assumptions. So this is probably the most important part of the lecture, and I said before, this is important for two reasons really. Firstly, it's quite a natural thing for me to include on courseworks and exam questions. No exam this year, but certainly I've set similar coursework questions in the past. So the thing here is that you've got an important topic that isn't purely mathematical, not calculations based. And secondly, if you can master these, I think you'll begin to push against what you can naturally expect from MSc dissertation students. We'll talk about graphical detection of each one of these core modelling assumptions and how these are violated. Now, I think this might be the first example of something where actually the graphical methods might be more important than the numerical methods. So in terms of the extra sum of squares principle then and these f-tests, so in the last lecture we saw that R automatically produces an f-statistic to test the overall level of fit. Now it's very possible this isn't necessarily so informative. In the last example, multiple linear regression, all this shows is that if you collect sort of 6 different demographic statistics, at least one of these statistics has some predictive capacity for the employment rate. So in formal terms, what you're doing is you're comparing the model term against all these x variables, and you're asking, does at least one of these x variables have some I? Now, this is sort of still useful, worthwhile doing to a point, so it's very possible that this won't itself give you much insight into the problem. The really important thing is this basic idea and framework can be greatly expanded upon. Okay, so you can sort of do this sort of nice and easy f-test that R and EVs do automatically, but you can do a whole host of more complex things besides, using essentially the same mathematics and the same set of coding and software. Necessarily, therefore, this can give you a lot more insight. So in general terms, for a t-test, what you're doing is testing the significance of individual parameters. Now the f-test, what you're doing is testing the joint significance of multiple parameters. Okay, here, t-test, multiple parameters, f-test, and the idea of the f-test also is that you are comparing competing models. For instance, beta 2 equals beta 3 equals 0. And the second equation at the bottom of the slide is that the first model there, model 0, sits inside model 1. The terminology is that these are nested models. So this is the test that is conducted automatically in R, so and in EView. So this is just testing, does at least one of these x variables y, we don't necessarily know which one, but at least there is something here that is going on. And the point here is that whilst this is sort of worthwhile to a point, actually much more that you can do here with the same mathematics and the same set of coding and computer software. In terms of the extra sum of squares principle then, so again we've got nested models, so the simpler model, model 0, imagine this sort of sitting inside model 1 in some sense. The second set of parameters are equal to 0 in model 1, then to model 0, and I think the easiest way to sort of think of this is just model 0 sitting inside model 1, hence the name is models. It's exactly like more mathematics. The idea then is to test whether the extra variation in the data that model 1 explains, literally the extra sum of squares, hence the thing, is statistically significant. So is there any extra information in the additional 1 compared to the simpler model in model 0? What you've got in model 0 is a more complex model, and there's more going on here than just a constant term. Same basic idea. Is there a statistically meaningful extra sum of squares, extra information provides, and you're not constrained to just have this sort of simple comparison that we have on the previous slide. You've got a more complex comparison here, more going on in model 0, and additional complexity in model 1. So if you look at the previous slide, what's going on here with this extra sum of squares principle is that if you're comparing the simple model 0 to the more complex model 1, this is equivalent to testing the m, what are called linear restrictions, just that the rest of the last m beta values are all equal to 0, and so that the last m x variables don't have any impact at all upon the y variable once you include all the things in model 0. So in terms of formal mathematics, what is really going on here is something called linear constraints, and it says that you can use the same approach to test more general linear constraints, not just that these beta values in equation 1 are all equal to 0. So what is going on here is some difficult mathematics involving something called Lagrange multipliers, but the underlying idea is remain relatively simple. So throughout what you have is a simple model 0 and a more complex model 1, and you're just asking statistical evidence that model 1, model 0, so that there is additional worthwhile information and extra sum of squares provided by the more complex model 1 compared to model 0. So it's not just that all the parameters are equal to 0. So in the example at the bottom of the slide, you've got that beta 2 equals beta 3, linear constraints. It's not that the thing is necessarily exactly equal to 0. Same basic idea throughout. What you've got is a simple model 0 and a more complex model 1. So it says there that model 0 has m constraints, or equivalently m fewer parameters to estimate. Model 1 is larger and there's no parameter constraints, and the idea is that essentially the model 0 sits inside model 1. You've got this sort of structure like Russian nesting dolls, so that if these satisfied, the two models are the same, and model 0 sits inside model 1. So easy case is that the additional m parameters are all 0, which you've got there in case 1. Now you can have more complex cases. So here what we've got in this sort of second example here is that 2 equals beta 3. Now m equals 1 constraint, i.e. that beta 2 equals beta 3. You need to have beta 2 equals to 0. The thing is equal to 0. There is what is called a linear constraint, just a fewer parameters in model 0 compared to model 1. Again, model 0 is simple, model 1 is more. So with this extra sum of squares principle, the F statistic always has the same form, and the idea remains the same throughout. So you're asking, is the extra sum of squares in the data that is explained by the larger model statistically meaningful? So is the extra variation in the data explained by the larger unconstrained model statistically significant? And by sum of squares or variation, so these might sound complex statistical terms, it just means information in some sense. Now what I've got in the next couple of slides is some manipulations in terms of the R-squared statistic and the F statistic. Really the main point, I think, is the formula that you get 2 slides time on slide 2.4. Okay, so that is really the main point to get to, and as a mathematician I had to include some of the workings out, but really the main thing is that you can remember and use the formula that's contained on slide 2.4. So back to the maths then. So the F statistic is expressed as follows in terms of the difference in residual sum of squares divided by the difference in the residual degrees of freedom, and then on the bottom line of this fraction is the residual sum of squares of the larger model divided by the residual degrees of freedom of the larger model. So again, what we saw in the last lecture is that the F statistic can be written in terms of the R-squared statistic, and we're going to sort of expand on this idea in the next couple of slides. And really the main point is that you can remember the formula that's on the next slide, slide 2.4. Okay, so there's some maths here, but the main point is equation 4 on the next slide. So extension of this idea, so the F statistic in terms of the R-squared statistic, so you've got the same bit of maths going on underneath it all, but actually it's a more general idea known as the extra sum of squares principle. So if you start with so it's just the difference in the residual sum of squares over m, the on the bottom line. Now you can write sum of squares components in terms of the sum of squares. They cancel something that is written in terms of the difference of the R-squared statistic over the minus the r squared over the